Okay, hi everyone. Today the seminar is about linear programming, simple methods. First one, the introduction. Second, application of linear programming. Third, standard form of a linear programming. Fourth, geometry of linear programming and problems. Five, definition. And finally, programming and simple methods in MATLAB. The reference that I use in this seminar, there is the two books, Engineering Optimization Theory and Practice for editions. There is in the chapter 3, and the Advanced Engineering Mathematics 10 editions. First one, the introduction. Is important to know that the linear programming is an optimization method that is applicable for the solution problem with the objective functions and constraint appear like linear functions. The constraint equation we can see with equalities or inequalities. Second, application of linear programming. There are many applications of linear programming, and in this case I am going to put this example about of the oil refinery. We know that the oil refinery need to buy oil, and these can get for different sources, different composition, and different price. And then the other important part is after buy oil is to manufacture different products and create like such as aviation fuel, diesel fuel, or gasoline. But for create this one, we have many constraints. First one is the quantity of the crude that are available, and the second is the capacity of the refinery to produce particular product. At the final, the idea that what is the important for the linear programming is to get the maximum profit, and for this we need to know that the maximum profit are relation with the mix of the purchased crude oil and the manufactured crude products. It means that the linear programming permit to get a maximum profit in this case, or in other case a minimum on a specific case. There is number 3, the standard form of a linear programming. The general linear programming problems can be stated in the following following standard form. There is the scalar form, there is a function, in this case the minimize, there is a function, and there is in subject to the constraints. If we can see C, B, and A, they are non-constant, and X are going to be the decision variable that we need to calculate. In the matrix form, the function, the minimized functions, and there is a subject to the constraint 8x equal b. We can see the difference how to make in matrix form. One important is to the characteristics of the linear programming problem. Say are first, the objective function is on the type minimization type. Second, all the constraints are equality type. Third, all the decision variables are non-negative. I'm going to explain this one. It is very important to know that any linear programming problem can be expressed in standard form by using the following transformation. First one, it's important that note the maximization of the function is equivalent to the minimization of the negative of the same function. What it means, for example, this is the minimized functions, and it's equivalent to the maximum, that it means the negative of the same functions. Consequently, the objective of the functions can be stated on minimization form in any linear programming problem. It is important to know that in most engineering optimization problems, the decision variable represents some physical dimensions, and the x variables there will be no negative. However, in many cases we can search unrestricted variables such as positive or negative or zero values. In this case, the idea is to write to this x rating indifference of two non-negative variables. That it means that, for example, this one that it represents negative, we can write in these two difference in a rest of to this value, that they will be both together are greater than 0. And the constraint in many cases appears less than less than or equal to type of inequality. And for example, we need to add a slack variable. These are going to be the slack variable to transform this inequality to to equality equation. How can we make that? We add this xn plus 1 value. Similarity, for example, if we have inequality from greater than or equal to, that in this way we can say the same of the last example, but with negative slack variable. And this x n plus 1 is non-negative variable that is known as superfluous variable. It can be seen there are m equations of about in the n decision variables in the linear programming. We can assume that m is less than n, for example. But what happens if m is greater than n? It would mean there are redundant equations. How can know where are the redundant equations if with the rest of n minus n? What happens if the m is equal to n? It means there is only a unique solution. There is and there is impossible to make an optimization because it have only one solutions. M less than n, it means that there is undetermined set of linear equation. It means that there is infinite number of solutions, and the idea of our linear programming is to get one solution that satisfies the equation, or the optimal solution that we needed to satisfy the problem that we have. For we are going to talk about the geometry of the linear programming problems. It's important that the program we only have two variables that present a simple case. For the solution that can be obtained elementary graphing method. This method is to get a physical picture and to get the response about these pictures. In this example, a manufacturing firm produced two machines part using lathe milling machines and grinding machines. There are type of machines that can produce two different parts of machines, and it shows that the time that this machine can produce each machine part 1, it means that 10 machine part 1 can produce in 1 minute the lathe machines, and the second part of the machine can produce the same machine lathe in 5 minutes. In the same way, the milling machine and grinding machines. And this column it shows the maximum time available per week in each machine, and at the final we can see the profit that create of in each machine can create. In this case, the three machines create one machine part 1, we can create 50, and the other one we can 100 is the profit of in 1 minute. No? The idea is determining the number of parts of 1 and 2 to be the manufacturing per week and maximize the products. It means the idea is to in 1 week how many parts can create of machine part 1 and machine part 2 to create the maximum profit. These are the pictures. First we need to create the equation of this one. If we can see the equation of lathes, the first equation is 10 machines part 1 and second machine part 2, we can create less than 2,500 minutes. In the same way, the milling machine can create 4 and 10 machine 1 and machine part 2 in less 2000 minutes. And finally, the grinding machine can create X and Y number of machine part and machine part 2 in available time for 450. We know that this number, the quantity of the X and Y part of machine are going to be obviously greater than 0. There is another restriction that we have. And the final, we know the profit of the machine that we are get if 50 $50 we receive for producing 1 minute, and $100 have to for 1 minute with the second machine. How many quantity of this machine need to produce in this available time to maximize the profit? Now we can get the result above this picture, above this equation. In the first, we can see that the equation number 1, when y is 0, we can get in x 250. That is letter B. And in the same way, if x is 0, y will be 5. That it will be letter A. In the same way, we can create the same for the two lines. E2, we have the letter E, C, and D, and the last one, E and F. If we can see, our objective is we can find these are going to be the feasible solution. All these pictures there is that have a relation, we can get the shaded region. Here are going to be all the possible solutions that we have for this problem. The idea is to get the maximize the profit functions. For that reason, it's important to know the counters of the objective function are defined by this linear equation, no? In order to the price, in order to the profit that gain for per minute, no? We can get now, if we the maximum value of the largest case, objective function line has at least one point in common with the feasible region, and we can see the optimum solution that are going to correspond in this case are going to be in the point G. That it means that in X we can create a 187.5 part of the machine part 1, and the machine part 2 are going to create 125. That the profit is around 2021 million dollars. And this one we can know that this one only one point touch in the letter G. And but what happens if the equation of the profit change? It means, for example, if the profit rates for the matching parts are 1 and 2 are 4 and 100 instead on 5 and 100, we are going to have this picture. And where is the difference? If we can see the maximum profit that we can get in the last equation, we can get this only this point. But what happened in this picture? We can know there are many possible solutions with this equation. It means there is not only one possible solution. Other way that there is possible to do is, in order to get the equation, we don't have the feasible region may not be closed convex. We mean the closed convex when these are going to be closed convex, that all the region are make a feasible solution that are close. That in this case, if we can see the possible solution are very extensive, and for that reason, in this case, the profit it means that it can be increased infinitely, and without the value of the feasible region. The other extreme is when the constraint set me set may be empty. It means that there is no have a equation or have problem with the constraints. And the final is when the last possible case is when the feasible region consists only in a single point. It means that if we can make optimization because there is only one solution. Thus, the linear problem may have 5 different solutions. First one is the unique and finite optimal solution. Second, the infinite number of optimal solution. Third, an abundant solution. Fourth, there is no solution. And final, there is a unique feasible point solution. Important definition that we have in this topic is a feasible solution. There is a linear programming that any solution satisfies the constraints. It will mean when this one is called a feasible solution. The basic solution is a basic solution in which n minus m variables are set equal to 0. Basic solution can be obtained by n minus m variables to 0 and solving the constraint 5.1 simultaneously. And basic feasible solution, this is a basic solution that satisfies the non-negative condition of equation 5.2. Obviously, all the time we need to be greater than 0. Optimal solution is when we optimize the solution, we can get one or many solutions that are optimal solution of the problem. The convex X is about of the area of the solution of the feasible solution, and we can know there is a collection point in each part of the convex picture, and we can say any two pictures that we can find here, we can go belong to, in this case x1 or x2 belong to S. And for example, what happened, these are mean convex solution. It means that if you draw a line in each part of this one, we are going to touch every point in the line that you do create. But what happened where it's not convex, for example, in this case, for example, you can draw one line in the letter A to letter B, and we can find, in this case, we can get the feasible solution, but in this part, the solution, there is no part of the solution. It means this value of this, there's not part of the solutions, and we can find the same in those pictures. We can draw a line here, and line here, and line here. And simple methods, is the important part that we are going to learn here. At the first time, we have the objective functions, and this function is subject to the constraints. These are the constraints, and we know that all these constraints, they are going to be greater than 0, greater than or equal to 0. This is an example. First we get these objective functions, and we are going to get these constraints. Both of these constraints are going to greater than equal to 0. The first part that we need to do is, for example, in this case there is a maximization problem, but if we the first thing is change the sign of the objective function to convert it to minimization problem. It means all are going to work to minimization problems. And the second, for example, if the change of the sign of the inequality, where it is important to change the sign of the inequality if they are necessary, in order to obtain non-negative value of b. This is the example. For example, in this case, there is b is negative, but we need to know to change this thing because we need to have a positive value. For that reason, we change this one. In our case, in this example, we don't have this problem because every value that we have in the right of letter b are positive. For that reason, the only things what are going to do is to change the maximizing functions to minimization problem, and we can get this result. Put the equation to add the slack variables, we can get this equation, and we know that x1 and x1 to x4 are going to be greater than 0. In order to have this equation, we can get our matrix, our table. There is a simplex table that linear programming. It's important to know that there are two different types of variables: basic variables and non-basic variables. The basic variables, they are a column that have only one non-zero. It means only you can see only one here, the rest are 0. And the non-basic variable, and in the other way, we can have numbers here. No, it's important to know that every simple table gives a basic feasible solution in order to obtain the settings of non-basic variable to 0. And now I'm going to explain how to select the pivot. The first rule is selection the column of the pivot. For selection the column of the pivot, we first select the first column with a negative entry in row 1. There's row 1, the first number that is negative that we can see the first number is minus 40, and these are going to be the first column, the first negative number in the row 1. Second, we need to selection the row of the pivot, and these are going to be divided the column that we select first. We select this column, and we are going to divide it to the column of b, and the value of this one, the less positive value, are going to be the row pivot. In this case, 60 divided 2 is 30, and 60 divided 5 is 12. It means that 12 is less than 30. Here it will be that these are going to be the first column, and this one the first row. We can see in this way. Then the next step is the elimination by the row operation, and for do that we need to give zeros above or below the pivot. In this case, only above. For example, we can create this one. For example, this is our pivot equation, and we know we can note if we want to create 0 in this equation, we can get the row 1, this equation, plus a row 3. We can get 40 plus minus 40 are going to be 0, and we can do this everything with this line, and the line 2 is row 2 minus 0.4 row 3, and we can get this result. Now after this result, we have the continue problem. We have a negative number here. We need to repeat the process. And now the next column that we have a negative, we are going to choose this column, and we are going to do the same process. The same process to divide 36 divided 7.2 and 60 divided 2. The result that we get is 5. It means and 30. It means this row, sorry, is the row that you have a less positive number, and we choose now our pivot equation, our pivot our pivot equation. Okay, in the same way, we multiply to get 0. In this case, we need to create 0 this one and 0 this one, and we make to row 1 plus 10 row 2 and row 3 minus 2 divided 7.2 row 2. Now we change the variable. Now we see that x1 and x2 are basic. It means that their column have only one known 0 in this case, and in x3 and x4 there are non-vexing variable. And the final, forget the solutions, we can get this equation. For example, x2 7.2 x2 are equal to 36. This one we can the result we can get 5, and 5x1 are going to be 50. We can get the result and we can have 10. If we use this 10 and 5 value of this variable, it will be replaced in the first equation. That there is to get the maximum objective function. We can replace and we put 40 per 10 plus 88 per 5. We can get 840. And this one we can be the same result that we have in zeta result. It means there is the maximum that now with this value there is the maximum point that we have to optimize the problem. And now after understand this process, we are going to make an example in MATLAB programming. In MATLAB, so there is the function. In this case, there is a minimize functions, and there is a equation that are subject to this equation. No, we know that x are greater than equal to 0. And for do this one, we need to separate to make in a matrix form. And there is we need to express the objective function in fx and ftx, and identify the vector the x and f. And we can get our variable are x1, x2, x3, and our function we have -1, -2, and -1. And our A matrix we have 2, 1, -1, 2, -1, 5, and 4, 1, and 1. And our B vector we have 2, 6, 6. In order to get this matrix, we create a MATLAB program, and we can get we put our functions, our A matrix, and our B result, and we are going to get 0, 4, 2. I'm going to show you this one in MATLAB. Okay, now in MATLAB we create the function, the A matrix, and the B. We can run, and we can get our result. That it means x1 it will be 0, x2 it will be 4, and x3 it will be 2. And the value of this one, the final optimization are going to be 10. We are going to do the same exercise that we did the first time. The first exercise we put the functions and the A value of the matrix, and we can get 10 and 5 and 8, 40. That are the result that we can get in the mathematical equation when we have in the exercise that we have of our example. Okay, that we can find that there are the solution. And the second problem that we have, remember that there are the equation, we put the same functions, and we have the results 10 and 5. Thank you so much for listening to the seminar.